Hello everyone, I'm Alfian and today we are going to solve the LeetCode challenge on the challenge number 111 called the minimum depth of binary tree. And for this particular challenge, given a binary tree, find its minimum depth, minimum not maximum, I'm sorry. And the minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node. A leaf is a node with no children. And this part of 9 is considered a leaf, and also 15 right here is also considered a leaf because there is no children. And if you notice of the 3-node structure right here, we have the value, which is the 9 as the value, and the left property, which is none, since 9 has none, and also the right property, 9 does not have any right property and left property at all, so 9 is considered as the leaf of a node. And if you look over the 3 node right here called the 3, which is the root of the node, we have the left property of 9 and the right property of 20, and it's also in the form of another 3 node. And the thing about leaf is the one that is not considered has the value of left and right, or the property of left and right respectively. For example, 9 right here, 15 right here, and 7 right here, which is the marking the end of a 3 node. And there is no descendant after each of every node, so that is called the leaf node. And for the input right here, we have and this part is visualized in array form, which is 3 and then 9, 20 and then 15 and then 7, but this part is null because it is supposed to be after the 9. Since 9 does not have any left and right property, then it is already also addressed as the null. And it's also confusing for us beginners, and so bear with me for throughout this challenge. And the output is 2 is because the maximum depth, not the maximum but the minimum depth of the node of each subtree is considered with the 3 and 9 respectively. So since 3 is also the root of the node is also considered 1 and the 9 is also considered 1, then it is returning 3. If you have to traverse over the 20 right here, let's say 3, 20 and 7, we got 3, and 3, 20 and 15, we got also 3. Since they are both 3 and this part is only as the value of 2 that marked with the marker right here, and this part is considered 2 and this part 3. If we traverse over 3, 20, 7 and or the 3, 20 and 15 respectively, we got 3 and also 3, and we have to find the minimum possible of the output. So that is why this challenge is about, and the output is 2 since 3 and 9 is the suitable value to be returned as the answer. And the function itself, which is called the min depth, and we are working with TypeScript. If you want to use something else other than TypeScript, then go ahead, and encourage you to do so. And for this function right here called the minimum depth, takes only the one parameter called the root in the form either of 3 node or null. And 3 node class already defined right here as a 3 node class, and the expected output is in the form of a number, and the output right here, which is representing by the number of 2. So this is the expected output of the function right here. And for the example 2 right here, we have 2 null, 3 null and 4 null and 5 null and then 6. What it means by that, if I happen to visualize this roughly, it is about like using the 3 node, drawing a 3 node like this part. I'm using a drawing. We have the node 2 right here, we have 2, and then this part is null, and we have the right property, which is 3, and also after the 3 we have the property of null. This is of what I am trying to comprehend. And we have the property, not the right property of 4, and then we have the left property of null from the left subtree, and the right subtree of the 4 is 5, and the last one, which is null on the left side, and the right side, which is 6. So that is the rough visualization of what we are trying to solve right here. And we have the minimum output, which is 5. Why is it 5? It's because we are traversing over the 2, 3, 4, 5 and 6 respectively. Since 2 is considered 1, 3 is also considered 1, 1 again and 1 again, and the null is not considered as the leaf, and 2 right here is also 2, 3, 4, and 5 is also not considered a leaf because there is a subtree that is not null. The only node that is considered a leaf is the one that has not the left and right property, which is the only 6 right here. So since 6 is the only leaf that available in the array, not the array but the 3-node structure, then the output is 5, which is from the 2 right here. Consider 1 equals 2, 3, 4, and then 5. So that is the minimum depth of the answer. Do take note that the null is not considered a leaf, and also the 2, 3, 4, and 5 is not considered a leaf because then again we don't have any left and right property null because 6 is existing and 4 also has 5 and 3 also has the right property of 4 and also 2 has the right property of 3. Okay, so let's solve this out by creating an edge case right here to check if the current root is null, represented by the exclamation mark in front of the variable of the parameter, then we need to return 0. Why? Is because we are trying to solve this by using the recursive call. When we are calling from the bottom up to the root node, to the parent node that we are calling, and we are starting from the parent node, and for the return we need to return at least 1 if the root is exists, which is 3 right here. Since 3 is exists, then 3 also counted as 1, and we need to traverse over the left and right property respectively. So we need to use an if check. If the root dot left, we are checking the 9 right here. If we have 9, then we need to return another min depth recursive call of the function itself called the min depth. We need to use the function of the min depth and process the left property and traverse over the process like this one. And min depth is in the root. If let's say if the root left is non-existent on this part, which is the left property of the 2, since left property is null, then we need to process the right property instead. Then we need to traverse over the right if the left is null. Also the same thing applies on the right side. If the right side is null, then we need to process the left side instead. Then we need to divert our way to traverse over the 3 node. Then we need to assign the root dot right, and then don't forget to add 1. Why? Is because we already know that if the root left is non-existent, then of course the right side is existing, and also the same thing also applies on the other way around. If the right side is missing, then we need to process the left side. Let's say the 3 is null, and the null right here is replaced by the 3, and the null is replaced by the 3, then of course the left property of the 2 is replaced as the 3, and the right property is null. Then we need to process the left side instead of the right side by checking the, you guess it, using the root dot. If the root dot right is non-existent, then we need to return another min depth by calling the its function, calling the root dot left, and then don't forget to add this by 1. What about if both nodes are existing? For the case of the 20 right here, we have the value of 15 on the left side and also 7 on the right side. It is very simple. Then we need to compare which one has the minimum returning value from the bottom to the up to the parent. For the 3 right here, since 3 has the same case, because 3 is going to be processed last, and we are starting from the bottom because we are using the recursive call. Let's say 3 is the last one that we need to process. Let's say 3 has the 9 and 20 respectively on the left side and also on the right side. We need to check which one has the minimum value or the minimum returning value from the return statement right here, and also +1, and also return on the right side. If right is non-existent, then we need to return the left side and then +1, directing from the bottom to the up. Directing from the bottom 1 and then 2. Same thing also applies on the right property, 1, 2, 3, 1, 2, 3, and this one is 1 and then 2. Since 3 of them, 9, 15, and 7 is considered a leaf, then we need to process from the every leaf possible. Then we need to check which one has the minimum value from both left and right. This part, which is the left property, we have only 1, and then 2, we have 2. And this part, which is 20, the right part, it has 20 has the 2, both respectively has the 2 from the 7 and 15. As we go up, then we need to add 1 again, since 3 is also being counted, then 3 is returned. And then we need to compare from the left and right property, compare which one has the lowest value or the minimum value. Since 9 has the minimum, which is 2, and 20 has the 3, then 9 is going to be counted and 2 is returned as the answer. How do we use that? Is by using the return, and we need to add 1 right here, and 1 you can use the end, return 1 plus math minimum or the math minimum first, math minimum method. Using the math minimum will return which one has the lowest value. Using the first parameter, which is the min depth, we need to recursively call the min depth again using the root.left, calling both sides, and then min depth again, min depth on the second property using the root.right as the parameter, and then we add this after the minimum method and then add +1. We need to check, since the min depth root.left is returning 1 from the 9 right here, and the minimum depth of the root.right is 20, not 20 but 2, since because of the 15 and 7, then 1 will be returned, 1 will be selected as the winning candidate from the first parameter right here, from the minimum, from the math minimum method, and we need to add this by 1, and then since 1 added by 1 equals to 2, then we need to return 2 as the answer. And for the 20 right here, if you were asking about 20 right here, it is also the same thing, since 20 has the 15 and 7, then the math minimum of the min depth of the root.left is already returning 1 from the 15, and also it is already returning 1 from the root.right, and since they are both 1, then math minimum will returning 1 because they are still the same thing. Where do we get the 1 from? It is from this part, from the both left and right, since they are both from the 15 from the leaf, they are both null from the left and right property, then this one is not being applied. This one is not being applied because root left is non-existing, and also processing the root right, since root right is non-existing, then returning 0, then it is added by 1, and it is already catched by the root.left check right here, because the first one from the leaf right here is checking on the left property first, and it is already catched by the if check right here, and we return this root.right, and it is equals to the 0 because root.right is returning null from the if check right here. Remember, we are using the recursive call, and then added by 1, then we return 1 as the answer from the leaf right here. Also the same thing on the 7, also the same thing on the 5, not 5 but 9. So let's run this code to see if it works. Yep, it took so long to submit our code, but we got the runtime of 4 milliseconds and the memory complexity of the 97, which is beating the 22% roughly, is because we are using the minimum depth recursive call, and it takes a lot of processing time. And I have one more approach to this challenge, is by using the breadth first search method. By using the breadth first search, or the BFS, and we are trying to store this using the array or the stack array. By using the BFS approach is by creating something called the array of the constant q node, and the q node we can, since we are using the TypeScript, then we need to define the q node, and we are need to define the q node as the root itself. The first assignment is the root itself, or the 3 node, and the second one, which is the depth that we need to assign. And we need to address this one by one is by creating a 3 node data type, and then the second data type, which is the number, which is the depth of the Q node. And we need to take this as the 2-dimensional array. Then we need to assign this using the square brackets and the first initialization value. Then we need to declare the first square brackets and then nested square brackets with the value of root on the first parameter of the first data type of the 3 node, which is accepted right here as the data type. And then the next one, which is 1, as we know that if the current node of the root right here, since it is already handled by the if root is null, then we need to return 0. If it is existing other than null, then of course we have to assign this as +1 initially, and we already assigned this as the Q node. And for the next one, we need to use a while loop while the Q node dot length is above 0 to check if, as long as the Q node is, the length of the Q node is not empty, or the 2D array is not empty. As long as it is not empty, then we need to process all of the Q node based on the Q. So we need to process the first one, and then we assign the last one if there is another node. Let's say we are processing the node 3 right here, and the node 3 will be assigned as the root of the node that consisting of the value, and then the left, and then the right. And root right here is already assigned as that, and we have the depth of 1. We are assigning depth of 1 as the array, and that is the Q node. And then we are trying to, as we already assigned this as the array to the array, then we need to try to define if it is not null, then we need to process the 9 as the we are assigning 9 as our Q, as our new Q from the end of the 2-dimensional array. But at the same time, we need to eliminate the first one from the array, which is the main root right here, which is the 3. Then we need to remove the 3, which is the root, from the array. Then we need to process the left property and right property of the node, and we are assigning 9. If it is not null, we are assigning 9 as our new array inside the 2-dimensional array on the end of the array, and also 20 right here because 20 is existing, then 20 is being pushed to the back of the array. 20 is being assigned. And also the same thing, if we have 15 right here to be assigned, and also the 7. But the main thing, if we already process the 9, let's say we are traversing over the 9 and we are processing using the while loop instead of the recursive call, and since 9 is already addressed as the root.left, then the while loop can destructure the array using the array of the Q node, and then trying to access the, if the left end property of 9 is already null, then we need to return the value instead of the 9. Then we need to return the depth to the top, added by the previous one of the first iteration of the parent that already calling the 9 right here. Let me explain this by using the code. We can use the constant destructuring the root right here, the root of the 1-dimensional array from the 2-dimensional array. We are abstracting the node, the first thing, which is node, and then the depth. Since we already know that the node is the root and the first element, which is the 2-dimensional array, then it is 1, and we are using the Q node, and then using the shift, and then using the exclamation mark. Why we choose the shift? If we look over here, we have the, on the MDN docs, we have the shift. The shift method of array instances removes the first element from an array and returns that removed element. This method changes the length of the array, and it mutates the array of the array right here. And we have the array, and then the first element we see the array.shift. The shift will remove the 1, which is the first element of the array, and then returning the 2 and 3 respectively. And if we happen to use console of the array, then the array will be returning as the 2 and 3 is because it is already mutated. It was mutated by the shift method. And the array.shift, after the shifting, the value that we already shift which is 1 right here, is stored onto the inside the first element variable. And if we happen to run this, let me refresh the page. If we happen to run this, we have returning the first element as 1, and we are returning the array as the 2 and 3. What if we have the 9? If we use the shift method, then 9 is being removed and 9 will be printed after the first line, and it will be printed as the first element variable. Of course, 9 is being printed right here, and 1 is remain stationary. Is because 9 is existing in front of the array or the first element. If we use the push by pushing the 4, if we use push method using the 4 as the parameter, then we have the 9, 1, 2, 3, and 4. Push method is by pushing an element inside at the end of the existing array, and it ultimately mutates the original array, and we have the first element of 5. Is because first element will returning the length of the output from the array push right here. So since we don't assign the first element to the array push on our challenge, then I will eliminate that from the context. So we only focus on the shift and push instead. So let's go back to our code, and for this exclamation mark after the shift right here, shift method, TypeScript sometimes tend to declare the shift as is possible to be null or undefined. As we assign the exclamation mark right here, we are telling the TypeScript that it is fine, and we already sure that the Q node array is not null at all, because we already assigned on the front right here from the initial value of the Q node. So we are basically telling the TypeScript that, oh, it's okay, it is not null at all, then you don't have to worry about it is being null. And we are using the exclamation mark after the shift method. And then the next one, the node right here from the Q node dot shift is by removing the root and 1 from the element, is by removing this one. Let's say the state from the before the shift is 2-dimensional array like this, root and then 1. If we happen to use the shift method, then it will be empty array like this, and the shift method will return the root and 1 as the node and depth respectively. Node is the root and the depth is the integer number of 1. And if we happen to use the console.log node and then depth, and then we return 0 as our placeholder, if we run this, and we have the standard output of the 3, 9, 20, 0, 0, 15, and 7 respectively. And then 1 is the depth. It's because the root right here is the head of the every subtree assigned from the root. Let's say if we use the node.value and let's run this, and we will only get the first one or of the head. Yep, we are only assigning the value, which is the 3 right here, as the output and 1 as the depth from the destructurization of the node and depth. And also the case 2 right here, we are only have 2 and then the depth of 1. And let's move this to the next part. We need to check if the node.left is exists, then we need to assign the node.left using the Q node, and then the push method. We are pushing another array, 1-dimensional array, into our 2-dimensional array of the Q node. We are assigning the node.left into our Q node using the node.left, and then the second element of the 1-dimensional array, which is the number right here, we are assigning another depth of 1, depth plus 1 instead of just 1. It's because as we use the shift right here, we are removing the 1 from the queue and we are processing the queue. But for this, it is contradicts with the while loop right here. Let's say we are using the while loop, queue node.length, as long as the length is not empty array like this one, like this state. Since it is not the initialization, we have the length of 1. Then we need to process this one, node.depth and node and depth, and using the shift, will remove the mutates the q node as the length of 0, but then since we are still inside the while loop, then the process should continue until the while loop stops, until the every segment of the code is already processed inside the while loop scope, and then the while loop will ultimately stops if the q node is really length is really 0 at the end of the scope. And we are using the depth. Since depth is already assigned as 1, then we need to assign another one because 9 is already existing from the node.left. Then we are assigning 9 onto our existing depth and then added by depth plus 1. And we can add another check again, is in the if check if the node.right, if the node.right, which the 20 right here, is also existing, then we need to q node again, q node.push, same thing as the left part. Is in the node.right, we are addressing the right node as the queue to be processed from the while loop, and depth plus 1, also depth plus 1. But before that, we need to check if they are both null, or in other words, if they are leaf, considered leaf. What it means by leaf is there is no left and right property of the current node. We can check if current q node has no left and right property or leaf, if it is considered leaf, by using the if check if both not root but node.left. Since we are processing the current node q right here, we are using the node.left. We are checking if 9 has the left and right property, node.left, and the node.right is empty or null. Then we need to return the depth instead. And that way, let's say we have only one node from our test case. We have node of, let's say, 1, and then node is like this, and then there is no left and also there is no right, which is represented by the null right here. And for the while loop check right here, we are processing the current node, which is the 1 right here, as the root, and then the depth of 1, we already know that the depth of 1. And then we check if the current node dot left is null, and also the same thing on the not right is also null. Then we need to return the depth, which is the 1 right here. And since on 1 is the only node that is existing from the while loop, then while loop stops, and then it stops because the q node is already processed from the q node dot shift right here. And then after the while loop scope already checked from the early return of the depth, then the while loop, then it will be returned from the while loop scope, and the while loop will stops because the while loop of the length is already equals to 0 because from the q node shift and the array destructurization right here. And that way we are returning 1 as our depth. Okay, I hope you understand this part. And then we are returning 0 if we happen to check if the node is not existing at all. We are only returning 0 after the while loop will stops. Okay, so I think that is enough of my explanation, and let's run the code to see if it works. I hope it really works, and let's submit the code to see if it makes any difference. So it's 8 milliseconds, double the time. So let's run this again, and we have 1 millisecond. So that is much improved from the first approach. And about the BFS, or the breadth first search, it's about returning early from the check right here. We can add a check from the tree. Let's say we are iterating over the node 3 right here. We are assigning 3 as the root, and then 1, we have root, and then 1. And we are destructuring the node from the depth, and root and depth from the q node and shift. And the array will be empty. The state array of the array will be empty. And then we are processing using the if check right here of the first if check. Since 3 has the node of 9 and 20, then the first if check will be irrelevant, and we are check the second one. since left is existing, then we need to assign left into our new node of the array as the array, and then the right side also assign as the array. Let me visualize this. We are removing the first one from the destructurization, and then the next one we are assigning 9 as the one-dimensional array, and then 20 as one-dimensional array. 20 with both values as the 2, using the def plus 1 because def already assigned as the 1 right here. And then we are processing the 9 since one root and one already removed from the first one. Then we need to process another q node of the first element, which is q node dot shift, and shift will ultimately removes the first element, which is 9 right here, and 9 is being processed and checking if the node left and node right is null. Since 9 already null as the left and right property of null, then we need to early returning the def, which is def of 2, into our answer, and the while loop will ultimately stops, and the whole function will stops because of the early return of the def right here. So that is the neat use of the breadth first search approach. And if you notice on the return statement right here, it is always pointing to the return, not just on the while loop, because while loop, if we happen to return using the early check of the while loop, is by using the break, either break or continue. But in this state we are using the return statement, so we are returning the whole process from the function, and we are returning depth as our answer right here. So the 20 will not be processed, 15 and 7 will also not going to be processed, unlike on the first approach using the recursive function, and then 9 and 3 will be returned as that. So that's about it. I hope you understand my explanation. If you still don't understand, you can ask me in the comment section, or if you have any better solutions regarding this challenge, tell us what you think in the comment section. Thank you for watching the video. I hope you have a great day, and I will see you in the next video. Goodbye.